Okay, this is lesson 7-1. We're talking about exponential expressions that are expressions that contain an exponent, like 2 to the fourth, 10 to the first, 2 to the negative second. All of these are exponential expressions because they have a base and an exponent. Okay, this says copy and complete the table, which you should do by pausing this and writing this on your paper first. Attempt it as a warm-up, and then I'll go over it. But it says copy and complete the table, and then make a conjecture about how the value of an exponential expression changes when you decrease the exponent by 1. As you move from this answer to this answer, what do you do to this number to turn it into this number? And it'd be the same to do it to turn this number into this number, and this number into this number, etc., all the way down. Same thing here. As you decrease the exponent by 1, what happens to the value? Okay? And then what do you think the value of 5 to the negative 2 is? And explain. So I'm going to give you a chance to do that right now. Stop the video and try it, and I will fill in the values. We'll be back in a minute. Okay, so we're back. I filled in the values with what they equal to. 2 to the fourth equals 16, 2 to the third is 8, etc. Okay, 10 to the fourth is 10,000. Powers of 10. You put a 1, and then whatever the exponent is, you put that many zeros. So 10 to the fourth is a 1 with 4 zeros. 10 to the third is a 1 with 3 zeros, etc. Okay, now, that might be all well for positive exponents. What happens when it becomes 0 or it is negative? This lesson is on 0 and negative exponents. So, what is the change from 2 to the fourth to 2 to the third? Well, to go from 16 to 8, we divide by 2. You could say, oh, don't we subtract 8? Well, as you'll see, subtracting 8 doesn't get you here from this value to this value. It doesn't hold. But this does hold. Divided by 2. 8 divided by 2 is 4. 4 divided by 2 is 2. Following that pattern, we get 2 divided by 2 is equal to 1. 1 divided by 2 is equal to 1 over 2, or 1/2. And 1/2 divided by 2 is 1/4. All of these are divided by 2. Okay? And what you'll notice then here is that 2 to the 0 power is equal to 1. Okay? And as you go into the negatives, you will see that just like here, 2 to the first, which is 2, and 2 to the negative first is that same 2, but on the bottom of the fraction, 1 over 2 to the first. Okay? 2 to the negative second, right here, is just 2 to the second, 4, but on the bottom, so 1 over 4. Okay? And you'll see that that's a big piece of today's lesson. Same thing on the other side. If we go from here to here, 10,000 to 1,000, you are dividing by 10. 1,000 divided by 10 is 100. 100 divided by 10 is 10. 10 divided by 10 is 1. 1 divided by 10 is 1 over 10. And 1/10 divided by 10 is 1/100th. And same thing, as I had said before, if you took 10 to the second power, 100, and you put that with the negative exponent, 10 to the negative second, you would get that 100 on the bottom. Same thing, 10 to the first is 10. So 10 to the negative first is 1 over 10. And of course, 10 to the 0, just like anything to the 0 power, is 1. Big ideas for today's lesson. What then is 5 to the negative second? Well, we can think of 5 to the negative second, just like anything that's not already a fraction, we can think of it as over 1. Okay? And by writing it that way, we can use the negative to take the reciprocal of the fraction. We can take 5 to the second and put it on the bottom. We basically invert this, flip this fraction, take the reciprocal of it, and when we do that, we use that negative up, and there's no longer a negative there. And of course, we want to further simplify that because we can do 5 to the second power, and we get 25 for 5 to the second power. So the final solution is 1 over 25. So our essential understanding here is for 0 as an exponent, for every non-zero number, let's say a, the base of a, then a to the 0, whatever a happens to be, whatever base it is, that base to the 0 power is equal to 1. 4 to the 0 power, 1. Negative 3 to the 0 power, 1. 5.14 to the 0 power, 1. Anything that's a non-zero base, we raise it to the 0 power, we get 1. And for negative exponents, for every non-zero number a as the base and the integer n, where we have an exponent that could be negative, we say a to the negative n is the same as 1 over a to the positive n, changing the negative to a positive by taking the reciprocal. So we have 7 to the negative 3. We use up that negative to put that 7 to the third on the bottom, 1 over 7 to the third. Negative 5 to the negative second. We're going to use that negative on the exponent up, but not on this base, just on the exponent. Use that negative, and we put it on the bottom without the negative. So negative 5 to the positive second power on the bottom, 1 over negative 5 to the second power. That's the main idea for zero and negative exponents. Okay, now it was suggested that we can't use 0 as a base. It said for any non-zero number. Why can't you use 0 as a base with 0 exponents? Okay, so the first property on the previous page implies this pattern. Watch, we said, okay, 3 to the 0 equals 1. 2 to the 0 equals 1. 1 to the 0 equals 1. Following that pattern, we would say 0 to the 0 must equal 1 as well. So we have this as somehow following that pattern. But watch this pattern here when we have 0 as a base. 0 to the third power, or 0 times 0 times 0, that's 0. 0 to the second power, 0 times 0 is 0. 0 to the first power is 0. Following that pattern, every time we get 0. And that would imply that 0 to the 0 power is 0. And it is not possible for it to equal two different numbers. 0 to the 0 power can't equal both of these, okay? We don't have a definition for this. 0 to the 0 power is not something that we have a definition for or that we can write as a number. It is undefined. Neither of these values is considered to be the answer to this, okay? Why can't you use 0 as a base with a negative exponent? Doing that, if we wrote that, let's give a quick example. 0 to the negative 3 implies 1 over 0 to the third, which is 1 over 0 times 0 times 0, which is 1 over 0. You're dividing by 0. Some of you already know this, division by 0, just like with slopes. Division by 0, and I'll type it out. Division by 0. Oops. Zero is undefined. Hopefully you remember this. Okay, division by 0 is undefined, so we can't have negative exponents on 0 either. Just an important point of clarification. Okay, so problem 1 is simplifying powers. What does this look like? Well, what is the simplified form of each expression? Problem 1a says 9 to the negative second power. How do we deal with this? Well, the definition of negative exponents says that we would take that base of 9 and put a positive exponent of 2 on it by putting it in the denominator. Okay, 9 to the negative second is 1 over 9 to the positive second. Essentially what we're doing is we're taking this 9 to the negative second, and you can imagine it as being over 1, and then the negative asks us to take the reciprocal of that. So the 1 goes on top, and the 9 to the second goes on the bottom, using the negative of the exponent in the process of flipping it. Okay? And, oops. So then it says, simplify. 9 to the second power is 81, so 1 over 81. Okay? What is example B? Example B is negative 3.6 to the 0 power. And what is any base that's not a 0, raised to the 0 power? It's equal to 1. Okay? Use definition of 0 as an exponent. Now, here's a question. can you use the definition of 0 as an exponent when the base is a negative? Can you have a negative base to the 0 power? Yes, you can, as long as it is non-zero. Is negative 3.6 a non-zero number? It sure is. So that's true for anything that's a non-zero number. Got it? So here's our got it problems. What is the simplified form of each expression? Well, let's go through them one at a time. But why don't you pause it and take it an attempt at it first. Pause it right now. I'll give you the solutions in a minute. If you're not pausing it right now, that means that you're not actually trying the got it problems to see if you've got it. And that's how you should be doing it. So you should be pausing this, writing the answer down for every single one of these 5 exponential expressions, and then restarting the video. So pause the video now, write your answers as best you understand them. Okay, so we're back. 4 to the negative third. The negative tells us to put it on the bottom as 4 to the third, so 1 over 4 to the third, and 4 to the third is 4 times 4 times 4, or 64, so 1 over 64. Okay, B, negative 5 to the 0 power. Anything that's any non-zero base raised to the 0 power equals 1, so it just equals 1. Okay, 3 to the negative second. Negative exponent says take that 3 to the second, put it on the bottom, 1 over 3 to the second, and simplify 3 to the second as 9, so 1 over 9. Continuing the same way, 6 to the negative 1 is the same as 1 over 6 to the first. 6 to the first is just 6, so 1 over 6. And finally, we've got negative 4 to the negative second. That negative in the exponent says put negative 4 to the second power on the bottom. You need to keep the parentheses there, okay, because what that really is saying is negative 4 times negative 4. And what is negative 4 times negative 4? Negative times negative is positive. 4 times 4 is 16. So there's a 16 on the bottom, 1 over 16. Now, we have as a mathematical idea that an algebraic expression is in simplest form when the powers with the variable base are written with only positive exponents. So if they tell you to simplify, what they're asking you to do is write it with positive exponents, which means that you will need to take the reciprocal if the exponent is negative. Here's some examples of this. Okay, problem number 2. We're going to simplify these exponential expressions. Remember what we just said, which is that we want to change all the negative exponents to positive by moving them essentially from one side of the fraction bar to the other, taking the reciprocal of them. So here's the first problem. A, 5a to the third, b to the negative second. Well, what you really have here is 5 times a to the third times b to the negative second. And what has a negative exponent? That b term, or the b part of the term. So we take the reciprocal of that. B to the negative second is 1 over b to the second. And then we simplify that multiplying 5a cubed times the 1 on the top and putting the b second to the second on the bottom. That's what we get. Just the b part moves to the bottom because that's the only base with the negative exponent on it. Okay? What about b? 1 over x to the negative fifth. Well, this is an interesting one to go over because you'll notice that x to the negative fifth, that's already on the bottom. We're not always putting the variable on the bottom. We're moving it basically from whatever side of the fraction bar it's on to its opposite. So since it's already on the bottom, it's going to move to the top as x to the fifth because we use up the negative part when we move it. So what do we get? We get, they're writing it as a division symbol, 1 divided by x to the negative fifth, and x to the negative fifth is the same as 1 over x to the fifth. So you have 1 divided by 1 over x to the fifth. And remember, what is it, keep, change you were taught. So keep the 1, change to multiplication by changing to the reciprocal, like that. Okay? And by the way, this is unclear. That shouldn't be written like that. That's just a glitch of this system. It should say x to the fifth. That was a typo. Anyhow, what you get is x to the fifth. Essentially, all you did here is you took this part and you moved it from the bottom to the top because of the negative exponent. And when you moved it to the top, you got rid of the negative part of the exponent. Okay? So those are the examples. And here's your got it problems. What is the simplified form of each expression? Okay? You're going to pause it here. You're going to write down your answers. Then you're going to unpause this video. Like I said before, if you're shortcutting this, if you're not doing this, then you are not doing the required practice. And for this distance learning, you're going to really struggle if you're not doing this the way that we're telling you to do it, because you need to get this practice in by trying these and seeing whether you're right or wrong. So pause the video now, and then unpause it once you have answers on your paper that you can check. Okay, so here's the answers to this. X to the negative 9, we're going to move that x to the 9th to the bottom, 1 over x to the 9th. Okay. For b, n to the negative 3 is already on the bottom. We're going to move it to the top, and it will become x to the 3rd. There's nothing on the bottom because it's just over 1 now. Okay. For c to the negative 3b, there's no parentheses here, so the only thing that negative to the negative 3rd power is on as a base is the c. So the c will move to the bottom as c to the positive 3rd, and the 4 and the b will stay on top. So you've got 4b over c to the 3rd. Okay. For d, a to the negative 3 is already on the bottom. You're going to move it to the top. That a to the 3rd on top. Now that you moved it on top, it loses the negative. Uses it up in the jump across the fraction bar. So you've got then 2a to the 3rd. And of course this one, e, what has a negative, n to the negative 5th. That n to the 5th will be on the bottom once you use up the negative and make that jump. What stays on the top? Well, if there's nothing left, it's going to become a 1. So you've got now 1 over m to the 2nd times n to the 5th. All right, so for this next example, you're going to be evaluating these expressions. Remember that evaluating them means calculating what they equal when given certain values for the variables, okay? And here it says, as an important note to start, when you evaluate an exponential expression, you can simplify the expression, getting rid of those negatives by moving that part of it to the other side of the fraction bar before substituting the values. That way you're never dealing with negative exponents on these values. Let's see what this looks like in practice. Okay, problem 3. We're evaluating these exponential expressions. As I just said, we are going to substitute a value in for the variables, and sometimes you want to simplify it first to make it easier. So let's take a look at the problems that they've given us. Here, what is the value of 3s cubed t to the negative 2nd, 4s is equal to 2, and t is equal to negative 3. Before we do this, let's take the negative parts, this t to the negative 2nd, and follow our rule for negative exponents, which is to move that to the bottom as t to the 2nd. Then what we get, here's their two different methods. First, you can simplify first. Let's look at that, where we move that t to the 2nd to the bottom. Then we substitute the values in. Okay. For s, we put 2, and for t, we put negative 3. And of course, when we do this, we need to follow order of operations, which means to raise this 2 to the 3rd power first. 2 to the 3rd power, 2 times 2 is 4, times 2 is 8. Then multiply by the 3. 3 times 8 is 24. Here we're saying negative 3 times negative 3. Multiply together twice and get a 9, so you get 24 over 9. This is a fine way to leave it for us. We'll accept it like that. Or if you turn it into a mixed number, 9 goes into 24 twice. That's 18. So you get 6 left over. And 6 over 9 simplifies to 2/3, so 2 and 2/3. The other method would be to substitute first. Okay, so you substitute these numbers in for s and t, and then we're going to now move things where they go. We're going to take this with the negative exponent and move it to the bottom. And you can see that it results in the exact same answer. So either method is fine. Okay. Now, what about the got it problems where we are, excuse my little marks for my answers that are written there. What's the value of each expression if n is equal to -2 and w is equal to 5? You're going to pause the video right now and you're going to attempt this. You can use either method, either simplifying first by moving things to get rid of the negative exponents or substituting first. Either way, pause the video now, write down your answers for these, check your answer against my answers after you have an answer of your own. So don't skip this part. Do this got it problem. Pause the video now, please. Okay, so what do we got? We've got n to the -4 goes down to the bottom as 1 over n to the 4th. And of course, the w to the 0 power is 1, so that's getting multiplied by 1, so that becomes a non-issue here. W to the 1st power is 1. Multiplying this by 1 just keeps it what it is, the identity property of multiplication. And when you substitute in -2 to the 4th power on the bottom, -2 times -2 times -2 times -2 is 16. Oops. So we've got 1 over 16. Okay. For this next one, what are we changing here? We're putting that n to the 1st power on the bottom. I choose to simplify first. And then we're substituting values in. So you substitute -2 in for n and 5 in for w. Doing order of operations, you get -2 to the 1st power is -2. Times 5 to the 2nd power is 25. -2 times 25 is -50. So we get a fraction -1 over 50. Okay, for C, n to the 0 is just 1 on top. W to the 6th power means we substitute 5 in for w, and we get 5 to the 6th power. 1 over 5 to the 6th power. That's a big number that you should be able to write that down on your paper as 5 times 5 times 5. Continue to multiply until you've done it 6 times, and you get 1 over 15,625. What about D? Well, you can see that the w is what has the negative exponent. That jumps the fraction bar to the top. As w to the 1st on top, or just w, and n is on the bottom. So w over n, or 5 over -2, which simplifies to, if you put the negative out front, -5 over 2. Okay? Hopefully you got those right. And then E, there's one last got it problem, which is it easier to evaluate this expression, n to 0, w to the 0, for these values of n and w by simplifying first or substituting first? Well, substituting first, you're going to be plugging those numbers in. Simplifying first, we would just say, this is 1 times 1. What's 1 times 1? It is 1. The entire answer is 1. And of course, what you think is easier is your opinion, but I believe it's easier to simplify these both to 1, because then we never have to even write numbers in there, because we just know that anything to the 0 power is 1 times this to the 0 power is 1. 1 times 1 is 1. Okay, and finally, problem number 4, where we're using an exponential expression to solve a problem. You notice that this is labeled STEM, which is science, technology, engineering, and mathematics. And STEM refers to the idea of applying these concepts to scientific or technological or engineering problems, whatever. Okay, real life problems. So they're very important, because this is the point of all of this learning, is to be able to eventually apply it to problems that we can solve. So here is the problem. A population of marine bacteria doubles every hour. So you are going to be able to guess that it's going to be a base of 2. We're going to be multiplying by 2 after every hour. Okay, doubles every hour under controlled laboratory conditions. The number of bacteria is modeled by the expression 1,000 times 2 to the h, where defining the variable, h is the number of hours after a scientist measures the population size. Okay? Evaluate the expression for h equals 0 and h equals -3. What does each value of the expression represent? So let's just break this apart and think about it for a second. If it says 1,000 times this, then this must have been our initial starting population of bacteria. This is where we started. Okay. Now, h is 0. Let's check this out. Okay. What do we know? We know that 10 times 2 to the h models the population. We know that we're needing to evaluate it for values of h is 0 and h is -3. And so our plan that we're going to do is we're going to substitute each value of h, first 0, and then -3 into the expression to simplify it. Okay, so we substitute 0 for h, given our original expression. 1,000 times 2 to the 0. What is 2 to the 0? Anything to the 0 power is 1. So we've got 1,000 times 1, or 1,000. What does that mean? That means after 0 hours, meaning right when the scientist measures the population size, at 0 hours, there is how many? 1,000 bacteria. Okay, the value of the expression for h equals 0 is 1,000. There were 1,000 bacteria at the time the scientist measured the population. What does it mean for substituting -3? Well, if h is the number of hours after the scientist measures the population and we're going into the negatives, that means 3 hours before the scientist first measured this population. So they're doubling in size every hour, so what we have to do is essentially say, okay, we plug in -3 there. We've got 1,000 times 2 to the -3, or 1/8. And what is 1/8 of 1,000? It is 125. What does this mean for us? It means the value of the expression for h equals -3 is 125. There were 125 bacteria 3 hours before the scientists measured the population. Okay, we have a got it problem for this, and it is on the next slide, and that'll be the last thing we're going to do for this lesson. All right, a population of insects is tripling every week, which explains the base of 3 here for tripling. The number of insects is modeled by this expression, 5,400 times 3 to the w, where w is the number of weeks after the population was measured. Evaluate the expression for w is -2, w is 0, and w is 1. What does each value of the expression represent? I'm going to have you pause this right now, and you're going to calculate this expression right here, for w equals -2, w equals 0, w equals 1, and then know what that stands for. So pause the video right now and calculate these answers. See if you can get what I will show you when you unpause after having calculated your answers. Okay, we're back. Hopefully you actually solved these. If you are trying to learn this, remember you're being tested on all of this. So skipping this now is only going to cost you in the test. Okay, here's the answers. We take, for the first one where w is -2, we take the original expression and we substitute -2 for the variable w. Simplifying, we get 5,400 times 1/9. 3 to the -2 is 1/9. And when we multiply these together, we get 600. What does that mean? That means that there were 600 insects 2 weeks before. -2 for weeks means 2 weeks before the scientist measured the population. Okay? Evaluating for 0, w equals 0, what do we get? We take the original expression, always write the original expression. Then substitute in 0 for w. 3 to the 0 power is 1, so we're getting 5,400 times 1, which is 5,400. What does that mean? Well, at 0, w equals 0. 0 weeks after it was measured means at the time it was measured, there were 5,400 insects at the time the scientists measured the population. And finally, calculating and evaluating for w equals 1, 5,400 times 3 to the w, always start with the original expression, substitute in 1 for w, 3 to the first power is 3, so we have 5,400 times 3, or 16,200. What does that mean? 1 is the variable for w, or the value for w, so that means 1 week after the population was measured, there were 16,200 insects 1 week after the scientist measured the population. Hopefully you got those right. Do any IXLs that there are, and do the uh, problems that typically are for homework. And you can check those answers on the lesson page that's posted. You should do that. We're going to collect the homework that's posted. It's a short quiz to show what you know, but you should be doing all of these problems whether you're turning them in or not, because the goal is to learn this. And you're in a situation where it's a little bit more difficult. You're at home and you're having a less uh, supported learning environment in that you're not in class with others that are working on the problems and with the teacher. So you need to keep up with this by doing these practice problems and not skipping them because you can get away with it. That will only cost you later. So please work honestly and diligently. Good luck. Hope these videos were helpful.